So I'm going to talk today about the QDX PCB revision 4, which arrived here a few days ago and which I've been testing, finalizing documentation and finalizing the firmware and everything like that. The main thing I'm going to talk about today is a new way of driving the forward bias current for the pin diodes during transmit, but there are a number of other minor changes to the PCB which I'll explain as well. I want to stress first that this is not the QDX revision 4, it's a PCB revision. All of the QDX PCB revisions have similar performance, similar functionality, and it's just incremental performance improvements that I make to the PCB when the opportunity arises, when I get feedback from the customers, where necessary, if there are component changes due to supply shortages and so on. So here is the revision for QDX PCB. They come on a panel of 6 and with grooves down between the individual pieces which easily snap off. And this is one PCB. I will just quickly talk you through the changes that exist on it for revision 4. So the first thing to do, there was a shorted wire down here at the end of C41 due to a design error in the revision 3A PCB. So the very first thing to do was to, of course, remove that error, so there's no longer a little cut required to remove that short circuit. Now, another thing that I've done on request was I have increased the pin spacing on the BS170s to 0.1 inches between each pin, and the reason for that is that some people like to use turned pin IC socket strips so that they can replace the transistors easily. Personally, I don't like to do that. I prefer to solder them in solidly, and I don't generally have a problem with blowing up BS170s anyway, so I don't find the need, but that was done for people who want to use sockets. Previously the pin spacing was 87 mils, now it's 100 mils. You'll also notice, or perhaps you won't notice, it's a very slight change, that the capacitors either side of the toroids here and this toroid here have been slightly widened further apart, and the reason for this was to make space for a future version for low bands, so perhaps 160 meters or 630 meters, perhaps even 2200 meters, where it will be necessary to stack two toroids together to get the necessary inductance. So by moving those capacitors slightly further apart, I've made space to be able to put together two T37-2 toroids next to each other to double the inductance. Now if I turn over the board, you'll see on the other side another change in this area. Previously there was the A03407. The 3407 was used as a reverse polarity protection switch. This is a revision 3A board, and you can see the 3407 here, A03407. It turned out in practice, and again not something that had affected me particularly, but it turned out that in practice that thing blew pretty quickly like a fuse. Immediately something went wrong and the rest of the circuit drew too much current. Quite a surprise, because the rated continuous drain current for that device according to the datasheet is 4.1 amps, derated to 3.5 amps at 70 degrees centigrade. So it's 3 or 4 times higher current capability than it's expecting to see in this circuit. So it's quite a surprise that it broke, but on the other hand it is a very small device, so it could get hot quite quickly. And so on the revision 4 board, coming back to the new revision 4 board, I've changed this P-channel MOSFET to an AOD403. It's a much more chunky P-channel MOSFET in a TO252 package, so it's got a much bigger heatsink here, which you can see is soldered to the board. And this has a continuous drain current rating of 15 amps, so it's a lot chunkier device, and hopefully that will be a lot more resilient to abuse than we've found with the A03403. Now, one more change was made in the area of the 25 MHz TCXO buffer amplifier. Previously, I had been using an NPN PNP transistor arrangement to buffer the 1 volt peak-to-peak output of the TCXO to about 3.3 volts peak-to-peak for the microcontroller and the SI5351A. It was found with reversion 3 and revision 3A, that there was loss of PLL lock. So if you listen to the QDX transmit during on another receiver during transmit, you would hear this occasional loss of PLL lock, perhaps once a second or once every 2 seconds, and it sounded like a popping in the receiver. And so this impacts the purity of the transmitted signal and probably reduces the amount of reception reports that you would get, or successful decodes of your transmission. So this was a bad thing, and it was solved in version 104 of the software by configuring the SI5351A in a different way. But that didn't really solve the problem at source. What it did was hide the problem. In order to solve the problem at source, I had to dig a little bit deeper into that. And what I found was that the amplitude of the signal coming out of the NPN PNP buffer was very slightly less in the revision 3A boards than it was in the earlier revision 1, revision 2 boards. And the reason for that was that I had to move this whole section containing the SI5351A and the 25 MHz TCXO from far closer to the microcontroller here to a little bit further away so that I could make space for the ADC chip, the larger ADC chip, the PCM1804, which is on the other side of the board. And because of those slightly longer trace lengths, I believe that there was more parasitic inductance and capacitance, and that's slowing down the edges of the 25 MHz waveform and making the amplitude slightly less, loading it more highly, and just tipping it over the edge of what the SI5351A does not like to see. It was not a problem with SI5351A versus MS5351M. Both versions of the chip behaved exactly the same way. So in order to solve that, what I've done is abandon the NPN PNP transistor, and instead I'm using a 7.4 series logic gate. Now these come in single packages, and I'm using here a 00 NAND gate. So it's a single gate in a tiny package about the size of a transistor. And what this does is it makes the 1 volt peak-to-peak signal from the TCXO into a very, very precise and full rail-to-rail 3.3 volt signal, which drives the SI5351A and the microcontroller here very happily indeed, and there's no more loss of PLL lock with or without the firmware changes in 104. So that really solves the problem at source, whereas version 104 reduced the frequency of those PLL lock losses by maybe a factor of 100, so you'd perhaps get one pop every 5 or 10 minutes rather than once every few seconds. So this is the real permanent, proper fixing the problem at source. And now, saving the best for last, I have made a very interesting development on the forward diode, pin diode forward biasing arrangements, which is the main topic of the rest of this video. Before I get on to that, I just want to also mention another topic, which is that on the revision 3, 3A and revision 4 boards, we have found through customer feedback that on some of the boards there was a lock-up, a latch-up in one of these two op-amps, normally IC7, this op-amp here. And that's manifested by having pin 7 and pin 1 at about 0.8 volts, whereas they should be at a mid-rail DC bias of about 2.5 volts. And what this does is ruin your image rejection of the superhet SDR receiver, and so you will have full reception of the unwanted image 24 kilohertz down the band, as well as the wanted signal that you're trying to listen to. And so on the few examples that we found of that, I mean, I tested quite a few QDXs here and didn't see it until earlier this week, that they, on those few examples, they exhibit that very strange op-amp lockup. at power up. And I was unable to find any firmware workaround that would hide this or work around it or unlock the situation. And so if you have that situation, the only thing that you can do is desolder these 4 DC blocking capacitors C71, 72, 73 and 74 and short them out with a blob of solder or a small piece of wire, and that resolves completely the issue. So previously on the schematic here, the DC reference for the instrumentation amplifiers was taken from the common mode reference output of the ADC chip, and which is all in accordance with good practice and the ADC datasheet application information and so on. But in our application, we can actually just get rid of these DC blocking capacitors completely and use the DC bias coming through from the trifilar transformer on the other side of the quadrature sampling detector. Now, I was worried that there would be potentially some loss of performance, such as a increase in the noise floor or something like that, and so I did some detailed testing on one QDX with and without shorted capacitors to make sure that there wouldn't be any problem. To do this testing, I use my calibrated 7 MHz signal source here. This is a self-contained unit with a 7 MHz crystal and adjusted so that it's got these 2 BNC outputs with 0 dBm output and -60 dBm output. Very useful for testing. And I use that with a bunch of attenuators. So I found some inline attenuators in the Dayton Hamfest this year and some more at Friedrichshafen, including a nice one which has a selectable 0 to 10 dB of attenuation. So I can use those to dial in any attenuation level that I want. And so in order to, so I feed this in at -60 dB, and I then get the audio output and feed that from the USB sound card and feed that into Audacity, which is a audio software, and make a few seconds of recording, do a spectrum analysis with FFT, 8192 point FFT and Hanning window, and then export that to a text file, import it into a spreadsheet and plot the graph. And here is the result of that, and you can see basically the blue line is the original revision 4 without the latch up. The green line is when IC7 has latched up, so there's no image rejection. And it might look superficially like this is an improvement because the green line here is 4 dB lower noise floor than the red and the blue lines. However, the actual peak of the signal reception at -60 dBm is 6 dB down, so the signal to noise ratio is impacted by 2 dB. So it's not an improvement. Now, the red line is with C671 to 74 shorted out, and as you can see, the lines overlay each other almost exactly. In fact, the red line is very, very slightly better than the blue line. That might be just limitations of the experiment, I don't know. But at any rate, shorting out those capacitors C71 to C74 has no impact whatsoever on the noise floor. Now, the next thing I did was look at the strong signal end of things, and in this case I'm using the 0 dBm output of the calibrated signal source and attenuation to bring it down to -12 dBm. So 12 dB of inline attenuation. I find if I use 11 dB of attenuation to inject a -11 dBm signal, then that's the point at which clipping occurs and you get horrible distortion. The whole thing gets covered in all sorts of spurious responses due to the clipping. So -12 dBm is the largest signal which can be injected into a QDX without overloading it in this case. So I did it again with an original revision 4 PCB without the latch up, and then with the caps shorted out, and again the lines overlay each other almost exactly. The red line with the caps shorted out is very slightly better than the blue line, but again that could just be differences in the measurement. It's a very, very slight improvement. So both the noise floor at the bottom end as well as the strong signal performance are not impacted by shorting out C71 to 74. And if you find that you have that problem, with image rejection, you can you can remove those capacitors with full confidence, knowing that it won't damage anything. Now, in the 105 firmware, which is going to be the default firmware for revision 4 PCBs, there is a new tool which actually sweeps the image rejection. So it does a signal injection from minus 30.5 kilohertz to plus 7 kilohertz around the USB dial frequency, and it measures the unwanted image. You should see something like minus 40 dB or something like that, maybe minus 50, minus 40. There's some variation depending on component tolerances, but if you see almost no image rejection, like in this example, then you have a problem with C71 to C74. I am going to be modifying all 1000 PCBs of the revision 4 manufacturer by removing these capacitors myself and shorting them out. So everybody who receives a revision 4 PCB will be safe in the knowledge that they cannot have that latching up problem. So now finally on to the main topic, which is the new pin diode forward bias circuit. And to rewind a little bit back a few weeks or even months ago to when I started doing development of this circuit and recorded a few video segments, the manufacturing was actually very slow this time, and particularly the shipping was very slow. It was delayed for 3.5 weeks due to COVID-19 lockdowns. And so we had to wait a long time to get the boards. Anyway, here we go. Enjoy the rest of the video. So here is the QDX digital transceiver, 4 bands, 5 watts. It's very high performance. There have been a very popular, very high number of sales. But there is a design issue, it seems. And this design issue involves these two resistors here, R2 and R4. Now R2 and R4 set the bias current through the low pass filter pin diode switching during transmit to about 35 milliamps on each diode. The top side of these resistors is connected to plus 12 volts by these two transistors here, and the issue is that 35 milliamps through 12 volts is about 400 milliwatts of power dissipation per resistor, and there's no way that those tiny resistors 0603 size are really rated for 400 milliwatts each. Now there haven't been, I think, any issues with this except for heat production, but still it's not good to have things operating out of spec. So why is the current requirement 35 milliamps so high? And the answer is because we need that for harmonic performance. Now here I have a dummy load in an Altoids tin, and there's a 1K resistor here to another BNC connector which is connected to my spectrum analyzer. And this is just an easy way of attenuating it. And the offset, the reference offset is such that I've calibrated the measurement here on the so that the top here is 37 dB, which corresponds to 5 watts. Now on the terminal applications on the transmitter test screen, when I press the T key, you can see that I get the spectrum here on the spectrum analyzer. So I've just frozen the screen here so that we can get some measurements from it. If you look at the peak here, is measuring 38.2 dBm, which corresponds to about 6.5 watts. Now, if I move across to the second harmonic, you'll see it's measuring 2.32 dBm, so it's only 36 decibels down from the fundamental. Now, the FCC requirement is that the harmonics should be at least 43 dB down from the fundamental, so clearly this is not good enough harmonic rejection. And here we have the third harmonic at minus 1.77 dBm, so it's still about 40 dB down from the carrier. So this is what happens when you don't pass enough forward current through the pin diode switches in the low pass filter. You get harmonic content generated by the pin diode nonlinearity itself. So it's essential to put through enough current to be able to get rid of that non-linearity and have the diodes functioning correctly as switches. And I've found through experiment that about 35 milliamps is where that happens. Here is a photograph from the spectrum analyzer when the 35 milliamp bias current is used, and you can see that the harmonic content is extremely low. We see the second harmonic at minus 55 dBc and the third harmonic minus 61, fourth harmonic minus 76 and fifth harmonic minus 72 dBm. So they're all very low and much lower than the threshold level set by the FCC and other regulatory bodies. So I could solve that problem of the high power dissipation in those resistors passing their rating by using larger SMD resistors which are rated to be able to dissipate 0.4 watts, or I could have powered smaller value resistors from the 5 volt bus of the QDX, but neither of those things would have reduced the power dissipation itself. You're still dissipating about 850 milliwatts for the forward biasing of the diodes. So instead of that, I decided to have some fun with a switch mode regulator powering the diodes at 1.5 volts through series resistors. Now, a normal linear regulator functions something like a variable resistor whose resistance is adjusted by a feedback circuit such that the output voltage is regulated to a fixed voltage such as 1.5 volts. The disadvantage of that is that all the unwanted voltage is shed as heat. It's all power dissipation in that variable resistor. The variable resistor is implemented as a power transistor with its resistance effectively varied by control with a feedback loop. By contrast, what a switch mode regulator does is it has a switch, an on-off switch, and the pulse width as a percentage of the duty cycle is varied such that the average comes out at 1.5 volts, the desired output voltage. And so we need a switch, and we follow that by a filter which effectively takes some kind of an average, as you see on my dotted line here. And the advantage of that is that much higher efficiencies are available because the unwanted voltage is not dissipated as heat, it's switched, and in a perfect switch you would have no heat dissipation whatsoever. But in the real world we have heat dissipation and losses, so we don't get anywhere near to 100% efficiency. Now, the disadvantage of switch mode regulators is it's quite hard to get rid of that switching completely, and if, for example, you switched to 100 kilohertz, you would end up with this filtered voltage regulator output having some kind of noise on it like that, and so it's quite hard to get rid of that completely. And so the plan here is to activate this switch mode voltage regulator to produce 1.5 volts for some much smaller value diodes to feed bias current into the pin diodes, forward bias current, but to only activate that switch mode power supply during transmit, so that there's no possibility of generating any switching noise that would disrupt reception. And so I started looking at some switch mode power supply ICs, and it quickly became clear that several things happen which are to our disadvantage. Firstly, when you have a high voltage ratio between the input voltage and the output voltage, the efficiency decreases considerably. And secondly, at low load currents, the efficiency also decreases considerably. And so this is a TD1410 IC, and you can see here on their efficiency diagram from the datasheet with a 10 volt input. At the 2.5 volt output level, compared to 3.3 volt and 5 volt, the efficiency is considerably decreasing, and it's just dropping like a stone here at low output currents. And I found a similar thing with whatever I looked at. So here is a TPS 562208, and this particular chart actually shows for 1.5 volts output, and you can see the efficiency is, for the different input voltages, the efficiency is lower at the higher input voltages, so higher step down ratio, and as you reduce the load current, the efficiency also drops off quite considerably. So here for a 12 volt input and 100 milliamp load, we see something like a 62% efficiency. Similar story for TPS 562201 with a 1.5 output, and again here we see an efficiency dropping off as the current drops off. So for example at 0.6 milliamps, which is about where we want to operate it, and 12 volt supply, it's about 78% efficient. Lastly, another example, MPS 2315, and at a 0.6 volts, the efficiency with 12 volt input is also considerably dropping off, as you can see here. So some time ago I saw this discrete 3.3 volt buck converter design, and I found that quite interesting. The website is in the description below, and so I thought, well, we're in the middle of a chip crisis here. It's often hard to get hold of chips, and if I use any of these switch mode regulator chips, the efficiency is going to be something like 70% anyway. So why don't I try designing my own circuit based on this push-pull driver circuit here, which is quite an interesting circuit actually. And so that's what I did. I ended up designing my own switch mode regulator circuit. So this is the final circuit that I came up with, and you'll see it has a P-channel MOSFET as the switch here, and that's the existing Q1 from the QDX circuit, and it also uses Q2 from the QDX circuit, an N-channel MOSFET. It generates pulse width modulation from a timer in the STM32. So the STM32 processor has plenty of spare capacity, plenty of spare RAM, plenty of spare flash memory, CPU cycles, and plenty of spare I/O pins. And we can use one of the timer outputs of that to generate pulse width modulation. I use an analog to digital converter input pin on the STM32 to sample the output voltage of the regulator and to apply a control loop in software that allows the software pulse width modulation duty cycle to be varied, and that will allow me to regulate to 1.5 volts. So I'm using 2 additional microcontroller pins. As I said, there are plenty spare. Then there is a Schottky diode here. This is a classic switch mode buck regulator circuit that you see, a P-channel MOSFET switch followed by a diode, an inductor and a smoothing capacitor. And then here I've changed R2 and R4 in the QDX circuit to 33 ohms, and that will result in a current, if you assume a diode drop loss over here, so 0.9 volts across the diode, that will result in diode current of 27 milliamps in each diode, and that will be about 25 milliwatts of dissipation per diode, so well within the specification of a 0603 size diode. Now the interesting part of the circuit for me, when I looked at the discrete buck converter on the internet that I just showed you, is this NPN transistor. Now he describes this circuit as a pseudo push-pull driver circuit for the P-channel MOSFET. And what I think that means is that normally with, and he uses an N-type NPN transistor down here to pull it down, but I'm using an N-channel MOSFET. The same principle applies. When I switch on that MOSFET using a signal from the microcontroller, I'm pulling the gate of this P-channel switch to ground and thereby switching on the P-channel switch. But what happens when I switch off? When I switch off this N-channel MOSFET, normally if I didn't have this transistor here, I would have a resistor pulling this gate up to the plus 12 volts, and what would happen is that the gate charge on the capacitance of that gate would discharge through that resistor, and the switch will switch off slowly, and you can actually see that on the oscilloscope. And if you allow that slow switching off process to happen, it's putting the P-channel switch, MOSFET switch, into neither a completely on nor a completely off state, and that is reducing the efficiency significantly. So when I did that, I found the efficiency, overall efficiency, was about 40 or 45%. Now, adding this NPN transistor, what this actually does is it ensures very, very quick turn off of the P-channel MOSFET. And it's interesting to think how that works. So when the N-channel MOSFET here is switched on, it's pulling the gate down to ground through this NPN, through this diode here, and the diode is a type 1N41448, so nothing particularly special. Now, what happens when this N-channel MOSFET is switched off? So now we assume here that the gate is still at ground potential, or very near to ground potential, because there's a charge in the capacitors of the P-channel MOSFET. So the emitter here is at ground, the collector is at plus 12 volts, and the base is pulled to plus 12 volts via this 10K resistor. So there's a current, a base current flowing through the base emitter circuit of the NPN transistor. This diode is reverse biased, and so it's off. It's effectively out of the circuit. And so what we have is a base current flowing through this 10K resistor, and that allows to switch on a collector to emitter current, which discharges this capacitance of the P-channel MOSFET and ensures that it switches off very, very quickly. And you can actually see this on the oscilloscope if you look at the input waveform and you look at the signal here. You can see that they follow each other very closely, whereas if the NPN is not in circuit, you see this very slow turn off, and it's delayed after the end of the pulse here. The important thing is not that it's delayed or widens the pulse, but the fact that it's a slope rather than a sharp cutoff. So when you have this NPN transistor in place, and as I said, you switch off the N-channel MOSFET, this conducts very briefly for a short period of time until the voltage here is eliminated, the voltage difference, and then the P-channel MOSFET is switched off. So it's a very, very cool circuit. He called it pseudo push-pull drive because you're pulling to ground via the N-channel MOSFET and then pushing to plus volts by this NPN transistor. Even though you're only doing it briefly until that charge disappears and the switch is off, it's sufficient to ensure a quick turn on and quick turn off of this P-channel MOSFET. So it's operating as closely as possible as a switch. Then initially I had a 2.2K resistor here in the base of the NPN, and if you calculate it, a 2.2K resistor with 12 volts supply across it is dissipating 5 milliamps of current, and for example, if it's doing that for a 20% duty cycle here, that will mean on average 1 milliamp of current is being spent when I pull this transistor to ground, when I switch on this transistor. And so that's wasting about 1 milliamp of current, and 1 milliamp of current out of what I measured through here of maybe 10 milliamps means that you're losing 10% of your current, losing effectively 10% of the efficiency because of that 2.2K resistor. And the design on the internet was designed for a much higher load current than I'm doing here, and with much larger power transistors here. So it's not in any way necessary to have to drive that much current through this resistor, and I can actually increase that to 10 kiloohms here, as I've done, and it reduces the wasted current which is pulled through to ground very significantly by doing that, to about on average 0.2 milliamps, which becomes of much less consequence. So that was one change that I made there. Now, when I've done that, I looked at several measurements. I looked at efficiency versus supply input voltage with a 1.5 volt output. And as you go down in input voltage, so you reduce the ratio between the input voltage and the output voltage, the efficiency increases. So just exactly the same as the IC datasheet efficiency curves. The other thing I did lots of measurements on was various different inductors. So I had some junk box inductors. This is a 400 microhenry inductor, and I had a junk box 200 microhenry inductor, and then I had 47 microhenry inductors, which are exactly the same ones used in the QDX kit as it stands now. And I measured all of these, and the higher inductances worked better, so I will have to find a suitable one for the final circuit. I also tested different pulse width modulation frequencies, going from as low as 12.5 kilohertz all the way up to 900 kilohertz, and I found that it's not terribly sensitive to it, but with the larger inductance, somewhere around 50, 100, 200 kilohertz is the optimum. Now, the peak performance I saw when I had changed that resistor to 10 kiloohms was about 74%, which is quite similar to what is seen for 60 milliamp load currents and such a high voltage drop from 12 volts to 1.5 volts in many of the IC datasheets. So it's producing a similar efficiency to the ICs. The great thing is that I require only 3 transistors. 2 of them I've got in my existing QDX circuit, so will be reused. The NPN transistor is also a part which is already used in the crystal oscillator buffer in the QDX. So all I really add is a few resistors, capacitors and inductors here, and so none of the components should be hard to find, and in the ongoing semiconductor crisis that's quite important. So I'll be able to reuse those the same components that I'm using elsewhere in the QDX mostly. So next I removed the 330 ohm resistors from the QDX circuit, and I replaced them with 33 ohm resistors to this new switching regulator. During receive, it's very easy for the microcontroller to switch off the pulse width modulation signal, so there's only a pulse width modulation signal during transmit. And I looked at the spectrum analyzer, the harmonic content on the spectrum analyzer, and it actually slightly improves the harmonic content relative to the original QDX. So now the third harmonic has improved, according to my measurement on this unit, from minus 61 dBc to minus 66 dBc. I can't see the fourth harmonic at all, and the fifth harmonic has gone from minus 72 to minus 74 dBc. So although the harmonic content is already very, very low, this does seem to improve it slightly more, and I think that that's probably due to this 10 microfarad capacitor here, which just reduces leakage around this path through the resistors, because normally one side is connected to the switch at the low-pass filter input and the other side is connected to the switch at the low-pass filter output. So by having a 10 microfarad capacitor here, you're just kind of preventing any RF leakage through here. Although there are series inductors as well and everything like that, so it's only a small leakage path, but we're talking really, really low signal levels here. I also looked at close-in pictures. This is before the change, so with an original QDX, and this is after the change, so with the switch mode regulator, and there's no evidence of any problems from the 100 kilohertz oscillation frequency. So the span here is 1 megahertz, and that means each one division here would be 100 kilohertz. And so you would very easily see if there are any spurious entries because of the 100 kilohertz oscillation in the switch mode regulator. So overall, it's I think a very good result. It will reduce the heat dissipation in this bias circuit from about 850 milliwatts to under 100 milliwatts in total, and so it will take about 3/4 of watt of heating out of the QDX during transmit. There are no hard to find components, and it's a very fun and elegant solution, I think, to make a discrete component switch mode buck converter using the existing microcontroller as the feedback loop and using existing components in the circuit with a few simple additions. So this is my development board, and you can see the transistors, or rather you can't see them because I'm using the proper SMD transistors from salvage from some QDX boards, and it's all soldered on a PCB ground plane. This PCB ground plane actually came out of my 2N2222A competition development of that project. And you can see I managed to solder some wires directly to the microcontroller here for getting the PWM output and the ADC input. So I'm very happy with how the project turned out, and it lets us completely solve that problem of the heat dissipation in these two resistors and reduce the heating within the enclosure by 3/4 of a watt, which should help for cooler running during transmit. So the next job will be to, for the next PCB revision, include all of those components on the PCB and source suitable components for the ones which are not already in the parts list of QDX. So here's how it looks on the oscilloscope screen. The blue trace is the voltage after the P-channel MOSFET switch. So at the drain of the P-channel MOSFET where it connects to the diode, and the yellow channel is the output voltage, which is just under 1.5 volts. The output voltage, as you see, is constant. Now, if I change the input voltage here, so if I reduce that input voltage, you can see that the output voltage, the yellow trace, remains at 1.5 volts, and the peak here is coming down, but at the same time widening, which it has to do. So it's varying the pulse width in order to regulate the voltage, the output voltage at 1.5 volts. And that goes on quite well until you get down to 3 or 4 volts, and at 3 or 4 volts the waveform starts to get a bit curved, as you see there, and it can no longer regulate the output. This is because the threshold voltage of MOSFETs is 3 volts from the gate to the source. And so finally, here we were in late September, and the boards finally arrived, and you can see how I implemented these additional components for the switch mode power supply up here near the output transformer. And I did do plenty of testing on a development unit to make sure that there was no impact from having these components so close to the output transformer. And so, but that was really the only place on the board that there was for them. So we have here the inductor for the Buck regulator, Buck switch mode supply, and an input capacitor of 10 microfarads and an output smoothing capacitor of 470 microfarads. Those 3 components are on the top side of the board, and all of the others are on the bottom side. So there's an NPN transistor, a P-channel MOSFET, N-channel MOSFET, and of course the Schottky diode here. So the first thing to do was to build one of these and make sure there were no problems and that it worked properly. And here is my assembled QDX Revision 4 board, which I've done all the testing and final firmware development on. You can see that all the components are in exactly the same positions as they were on the Rev 3 and Rev 3A boards, the only addition being these 2 capacitors and the inductor for the Buck regulator up here. So what about the performance of this? So the first thing to note is that there is a new setting in the band configuration screen called the pin forward bias, which is specified in milliamps, and this basically, of course, just as it sounds like, it's the number of milliamps which are going to be fed into each of the 2 pin diodes, one either side of the low pass filter, during transmit only. So the switch mode power supply is not operated during receive, although personally I had it operating during receive for quite a few weeks and was operating it. I didn't see any interference products at all from it, but not wanting to take any chance, that is disabled during receive, so it's only active during transmit. Now, effectively, it does a calculation of the voltage which it needs to regulate in order to fix the current through the pin diode up at this certain value that you specify in this band configuration screen. So it's basically a constant current type of device in the way that it's implemented. And my first attempt of this went spectacularly badly. And you can see on this graph here that the target SMPS current through the pin diode was not very well matched to the actual measured current through the pin diode. And so I had very much oversimplified my calculation of what the voltage should be for a desired current. So it was of course more complicated than I had thought it would be, and we have basically plus 5 volt supply here, which is coming through a 1K resistor, and that's on all the time. That supplies about 4 milliamps during the receive operation. And then we have a 33 ohm resistor on the other side with the voltage 1.5 volts, for example, could be more or less than that depending on the current setting, coming through from the switch mode power supply. And these basically both feed into the inductor L1, and they pass the current down through into the pin diodes of the low pass filter switch. And the same thing happens again on the other side of the low pass filter at the input or the power supply, the power amplifier side of the low pass filter. So it's necessary in calculating the desired current going through down into the pin diode to take into account both the current coming through here as well as the current coming through from the switch mode power supply here. And I had in my simple initial plan not thought of all of those details. Now, in order to calculate that current, you need to know, of course, 5 volts the resistance is, this SMPS voltage here, but you also need to know the voltage at this point. And it's not a simple matter of a diode voltage drop, because what you have downstream of this is essentially there's the resistance of the inductor, L1, and then there's the resistance of the diode itself, or the voltage drop across the diode itself, which is normally 0.6 or somewhere between 0.6 and 0.7 volts. And then there is another inductor, another 47 microhenry inductor, and then there's the voltage drop through the MOSFET down to ground, which is pulling the voltage down through this diode. And so there's a voltage drop across the diode here, but there's also a resistive voltage drop which is dependent on the current flowing, and that's because of the resistance of this inductor and this inductor and the on resistance of the MOSFET. So you end up with a situation where you have two components to determine this voltage. So of course I made some measurements and I recorded them all carefully, put them into a spreadsheet, got the spreadsheet to draw a graph, do a linear straight line best fit through the points and tell me what the intercept and the gradient of that graph was. Now of course this will only be for one particular device. Every device will have slightly different component values, but I think this will be a fairly minor consideration. The main important thing was to take into account all the different things going on here so that we can calculate properly what the voltage should be coming out from the switch mode power supply. Once that was done, I was able to set the current in the band configuration screen and measure the actual current through the pin diodes by looking at the voltages across the resistors and adding everything up. And I was able to determine that the actual current consumption through the pin diodes, the forward bias current through the pin diodes, and the target current specified in the band configuration screen exactly overlaid each other, as you can see on this graph. So this time my calculation was effective. Now, the next thing I did was make some detailed measurements of the SMPS efficiency, And you can see in this graph what I measured for both a 9-volt QDX and a 12-volt QDX. And the results were very much in line with what I had been measuring on my development unit. So that's very pleasing. Something between 70 and 72, 73% efficiency typically. This current consumption shown on the x-axis here is the total current consumption of both pin diodes on either side of the low-pass filter, and added together. So it's the actual current consumption that the SMPS is delivering into the load. Now, an efficiency of 70–72%, as I said earlier, is quite comparable with what you would find on most small SMPS ICs, and so it achieves something similar to that. And as you'll see in a moment, it's enough to really improve the heat dissipation in the QDX. So next I measured the power dissipation through an original QDX and made calculations on all the measurements I had made and plotted those results out on this graph. And you can see the blue line here is the original QDX power dissipation. This is a 12-volt QDX, and the red line is the total power dissipation when I'm using the new switch mode power supply as the supply for the forward bias current. I should mention that what I'm calculating and plotting here is the additional heat dissipation during transmit due to the additional current which is being pumped through those pin diodes during transmit. And when you calculate at 12 volts and with the known voltage drop across the pin diodes and the 330 ohm resistor, what you end up with is that the QDX, the 12 volt QDX, was operating just below a 40 milliamp per diode current. And what that means is that in total we were dissipating over 800 milliwatts of additional power as heat during transmit, just in order to forward bias those diodes sufficiently to avoid intermodulation. Now here is a similar plot for the 9-volt operated QDX, and I should mention that at 9 volts there's about 30 milliamps, or just under 30 milliamps, being pushed through the pin diodes. It results in a much lower heat dissipation of something like 450 milliwatts. Now, the reason for that is that we actually need something like 25 to 30 milliamps of forward bias current to avoid the second harmonic and even harmonic distortions coming in the pin diode. Now, because the circuit in the original QDX is quite simple, it's just a resistor to generate the necessary forward bias current rather than a constant current arrangement, what it means is that I have to choose the worst possible case, which is the 9-volt supply, and which results in a much higher current than we would actually need when it's operated at 12 volts. So that's why the resistor values were chosen so as to get this current consumption at 9 volts, somewhere just under 30 milliamps. So it's a really substantial power saving, particularly on the 12-volt QDX. And I can actually interpolate and calculate from my data measurements here that a 12-volt QDX would dissipate 856 milliwatts as heat just for powering the additional forward bias current during transmit at 40 milliamps per diode. Now we can set it to 30 milliamps per diode on 12 volts, and at that setting we will be dissipating in the new QDX revision 4 only 134 milliwatts of heat. So a massive saving from 856 milliwatts of heat to 134 milliwatts of heat. That's a saving of almost 3/4 of a watt of heat dissipation during transmit, just by using this switch mode power supply technique rather than the diode to drop the current, to control the current. Now, another way of looking at the data is to calculate the power dissipation through one of the resistors, R2 and R4. Now, as I said in the original introduction, the main concern here was that the power dissipation in those resistors was over 400 milliwatts. and was quite extreme for an 0603 resistor and obviously way beyond its rating. So how do we end up here in the revision 4 QDX? So with this very detailed, accurate measurement that I made on this board, I was able to calculate that the power dissipation as heat in the 330 ohm resistors on the previous revisions of the QDX operated at 12 volts with a 40 milliamp bias current through the diodes was basically dissipating 387 milliwatts as heat. Now on the new QDX revision 4, running these diodes at 30 milliamps, which we are able to do because we have now a constant current supply. It doesn't matter whether it's 9 volts or 12 volts or 7 volts or whatever, it will always pass 30 milliamps through those diodes. Now at 30 milliamps, the power dissipation in the 33 ohm R2 and R4 is each 22 milliwatts. So it's a massive reduction in heat dissipation in those resistors from 387 milliwatts down to 22 milliwatts. So I think we can safely say those resistors will not mind at all dissipating 22 milliwatts. And now here's a frozen picture showing what happens on key down. The horizontal scale here is 2 milliseconds per division. And so basically within 2 milliseconds of key down, of switching on the SMPS, the voltage on the output of the SMPS has practically risen to its stable final value. On key up, it takes about 20 milliseconds for the capacitor to discharge to reduce the voltage, to drain away the voltage coming out of the SMPS. Now, what we see in practice here on the transmit, on the PTT for 0.5 second key down, during transmit, which is on the transmit test screen in the terminal applications, the RF is started immediately on pressing the T button on the keyboard, and so there is no delay between them. But actually, when you look at how this really operates in WSJTX, now here I've pressed the tune button in WSJTX, and the blue trace is monitoring the actual RF output into a dummy load, whereas the yellow trace is monitoring at a much lower vertical resolution. It's half a volt per vertical division on the yellow trace and 10 volts per vertical division on the blue trace. And so what you see here is that there's a 0.1 second delay between WSJTX enabling the PTT, switching everything to transmit, which switches on the SMPS, and the actual RF starting. And similarly on key up, there's another 0.1 second delay before it releases the PTT and switches back to receive. So in other words, there's plenty of time, masses of time, to stabilize this voltage before the RF transmission starts. Stabilizing the voltage at the output of the SMPS takes about 2 milliseconds, but we have 100 milliseconds before the RF starts. So there's no problem there either. So that's about it. That's a full description of everything that's in the PCB revision 4. And as I said, the firmware that will be released with it will be 105. It has also the VGA output, the PS2 keyboard interface, and the 3 additional serial ports for anybody who wants to use those. But the main important thing as far as the revision 4 PCB goes is that you will need 105 in order to implement the control loop for the switch mode power supply. So revision 4 PCB should be run on 105 or above so that the power supply gets controlled properly. Thank you for watching, and as I said, we will begin shipping these nice QDX Rev 4 boards in the next few days. Every single one of them will be properly tested, flashed with the latest firmware, as well as the 4 capacitors C71 to C74 removed and shorted, so there's no possibility of the operational amplifier lockup. Thank you, bye bye for now.